What do postsynaptic potentials, EPSPs and IPSPs, become once created at postsynaptic membranes? How do they propagate along dendrites, and what is their role? Here is a neuron with two afferent glutamatergic synapses in red and two GABAergic synapses afferent to this neuron in blue. If now we record the activity of this neuron in whole cell configuration and current clamp mode to record the changes of potential, we record this compound somatic PSP. Somatic because we record it from the soma, and PSP for postsynaptic potential. So this is a depolarization. Now, if we add a blocker of GABAergic synapses, it means that the blue here are blocked and we record only the effect of the red ones. We record a bigger depolarization of higher amplitude than the green one here. It means that the glutamatergic synapse depolarize the membrane, and if the GABAergic synapses are active at the same time, it reduces the effect of the depolarization. Now, if we do the contrary, we apply blockers of the glutamatergic transmission, APV for NMDA channels, CNQX for AMPA and kainate channels. We record hyperpolarization of the membrane, which is not big, but here, and no depolarization at all. Now, the green one is in fact the sum of these two. And you can see here at the beginning a small hyperpolarization followed by a depolarization of smaller amplitude than the orange one. If we plot all the traces at the same scale, you see here, of course, that the depolarization without GABAergic synapses is larger, and the change of potential without the glutamatergic synapses with the GABAergic synapses only is a hyperpolarization. You see here that synapses are all along the dendritic tree and the soma here. These synapses are called axospinous because it's between an axon terminal and a spine. The number 2 is axodendritic because it's between an axon terminal and the shaft of a dendrite. And axosomatic for the 3 because it's between an axon terminal and the soma. Imagine that you have a lot of these types of synapses on the dendritic branches and the soma. How do they sum along the dendritic trees? And first of all, how do they propagate? Here we record the activity of a single synapse. The configuration is called whole dendrite because we are attached first to a dendrite and then a small hole is performed so that we have access to the whole dendrite. This is theoretical because it's very difficult to record the activity of a single synapse. But let's suppose we can do it. We would record this. First, in current clamp mode, we record an excitatory postsynaptic potential. I remind you that it's called excitatory because it's depolarizing, and when it depolarizes the membrane, it has a tendency to open sodium channels at the axon initial segment. So here is an EPSP, and underlying this EPSP is a current that we can record now in voltage clamp mode, and this current is an inward current due to the entry of sodium and a small exit of potassium ions. This glutamatergic current is short and inward, so there is a net entry of plus charges. After this entry of plus charges, how these charges propagate so that we can record an EPSP at the soma and then at the axon initial segment. I remind you that what is very important is what happens here in the axon initial segment, because this is there that the sodium channels can be activated and give rise to an action potential. How does this EPSP propagate? We now record at two sites, the dendritic site here and a somatic site here in whole cell configuration and current clamp mode to record changes of membrane potential. The synapse is on the dendrite here, far from the soma. This is the origin of the EPSP, and if we recorded here, we would have an EPSP of that amplitude at time 0. Then at time 1, when it's here, between the soma and the dendrite, and at time 2, when it's in the soma, how is the amplitude of the EPSP? Here the amplitude had decreased, and here in the soma it has decreased a lot. And you can also see that the rise time here is longer. So when the EPSP propagates, its amplitude decreases and its rise time lengthens. How does it propagate? What are the mechanisms? The plus charges that entered are essentially sodium ions. These sodium ions are here in the intracellular compartment, where there are a lot of other plus ions, the potassium ions, and they repel each other, so that they repel each other, and they go further down like that, with repelling each other. And that's how they can accumulate in the soma and then in the axon initial segment. But while they repel, there are also leak potassium currents in the membrane, so that now some potassium ions exit. You remember that the electrochemical force for potassium ions is to push them out. So some potassium ions go out, so we lose plus charges while the EPSP propagates. And at the end, of course, the amplitude is a lot decreased because there are less plus charges than at the origin of the EPSP. We say that this propagation is passive because it's a passive repel of plus charges, and decremental because it loses in amplitude while propagating. It should be noted that plus charges propagate in two directions. They don't only propagate downstream here towards the axon initial segment, they also propagate upstream, of course, because there is no reason that there is a direction of propagation. But upstream, we are not interested by it because what is interesting is what it does at the axon initial segment. We just saw how a single EPSP propagates. Now, what happens when you have two here, but it could be also much more than two glutamatergic synapses on the dendritic branches? So the one alone here is recorded in the soma and has the amplitude here in dotted lines. The synapse 2 alone, when recorded in the soma, has this amplitude here in dotted lines. But when the two are active close in time, they arrive at nearly the same time in the soma. And how do they sum? And we see here the resultant, which is exactly the geometric sum of 1 plus 2. We say that there is linear spatial summation of EPSPs. Why is this sum linear? It's because the two synapses are not on the same branch, so there is no interference between each other, and they sum geometrically here in the soma. This is called spatial summation because the two synapses are located in different points of the dendrites. They are not located close to each other. They are on different branches, so this is called a spatial summation. There is a different form of summation which is called temporal. It happens when the same synapse is active several times in a row. So now let's record the effect of this synapse in the soma, whole cell recording, current clamp mode to record the changes of membrane potential, and the synapse is active once, twice, and 3 times at very close times. So it means that the second time it's active, the first EPSP is not yet back to normal, to control value, to basal value. And the second one and the third one also happens when the second one is still decaying. This summation is called nonlinear, so you immediately see that the third one is not equal to the 3 times the first one. It's less than that. Why? It's a question of driving force. So the current underlying the EPSP is a cation current. It equals G, the conductance of the membrane, multiplied by the driving force. The equilibrium potential for cations is around 0 millivolt. So when membrane depolarizes, it goes closer and closer to the equilibrium potential. If we put the equilibrium potential here, 0, and you have here the depolarization. When you depolarize more and more, you go closer to this equilibrium potential, and the driving force decreases. Therefore, the current is decreased and the amplitude of the resultant EPSP is decreased. This is the nonlinear temporal summation of EPSPs.